right, good evening, everybody. Thanks for joining me today. We'll be talking about running Hive queries in the cloud. My name is Neeta Dembla. I work with HDinsight. I'm on the Hive team, specifically focused on performance. I run benchmarks and study query plans and find problems and see ways of improving the queries. So today's talk, I will be focusing on how you can achieve the best out of your Hive in terms of query latencies. We will be more focused on the BI workloads, not so much on the ETL. This is a quick look at the agenda for today. I will start off with how you can deploy Hive in the cloud. Can I have a show of hands? Is anybody using Hive in the cloud today? Oh, quite a few people. That's awesome. And then we will go into some benchmarks that we've been running and where we stand today with Hive. And then after that, we will dive into the various components that help us get to those numbers. The other one thing I want to point out is the two aspects to running a Hive efficiently in the cloud as such. One is the cloud topology and the deployment models. We will not be going too much into those. There is a talk right after this by my colleague Sid, and it's focused more on the Google cloud platform, but those cloud deployment models can be applied to any cloud vendors. So we will be talking more about Hive and the data management side of things and the general guidelines that we follow before we run benchmarks. So to deploy Hive in the cloud, last year, HDinsight announced the data plane service. If you were there yesterday at the demo palooza, you would have had a sneak peek into it. The data plane service comes with a host of other services for managing your data, like data lifecycle manager. There's a data steward service, and one of my favorite parts is the data analytical studio that allows you to look at the queries that you run, see the patterns, and also it will give you some recommendations on how you can improve your queries. This can be deployed on any vendor. You can use Amazon, Google, Microsoft, OpenStack. The good part of the data plane service is that there are blueprints that you could use to deploy these services. So if you've ever used Ambari and have had issues, using these blueprints is an easy way or a user-friendly way to deploy your clusters on the cloud. And if your workloads need ephemeral clusters where you want to bring them up and down and just use them temporarily, but you want your data to reside, be resident on the data lake, for example, there is support for ephemeral clusters because the meta store and the data lake is part of shared services. Again, there'll be more about this in the next talk if you want to learn about it. And also, there would be a birds of feather session in the evening today on the clouds and operations, so you can go and ask questions about the service. The other options to deploy Hive in the cloud, HDinsight has its own HD Cloud and Amazon Web Services, and Microsoft also has HDinsight that's powered by HDinsight HDP. And if you feel adventurous enough, you can deploy your own HDP build on AWS, Google, or Azure. I did it a couple of years ago. It's not really for the faint-hearted at that point, but I'm sure right now it's a much better experience. But I haven't tried it recently. So I would, if you wanted to try maybe HD Cloud or data plane service, was probably your best bet. Next, we'll talk about benchmarks. I'll start off with a cloud benchmark. This was done by Microsoft on HDinsight. This is a TP-CDS benchmark. And most of you must be familiar with TP-CDS, but it's an industry standard benchmark. It has a bunch of, it has a good mix of queries. Some of them are quick reporting queries, others are deep analytical queries. This is based on a retail system with 12 to 13 dimension tables and 6 fact tables. So this is the query latencies. As you can see, 70% of the queries ran under 2 minutes, 40% actually ran under 30 seconds. And this was done on 100 nodes with the 100 TB scale, which is a massive scale that I'm aware of that has been attempted on the cloud so far. Oh, my battery is low. Sorry. Sorry, guys. The battery is low. Do you have a power connector here? The power connector. I have the power connector. I just need.
Let's see, what's this one?
Can I continue?
Yeah, go ahead.
Okay. So the key takeaways from the cloud benchmark by Microsoft was that Hive LLAP was the only engine that could actually run all the 99 queries. They also compared the performance with Presto and Spark. The Hive LLAP performed better than Spark and Presto. There's also text caching support. There's also text caching support with Hive LLAP, so you do not have to actually convert your data into ORC or Parquet to be used. CSV JSON data is also supported, and the performance of that on 1 TB was seen to be equivalent to the Hive LLAP. Hive LLAP also performs very well with high concurrency. They tested with 32 users, 64 users, and it scaled pretty well. So a little bit about our benchmark journey. We started the TP-CDS benchmarks a couple of years ago. With HTTP 2.5, we compared 2.5 Hive 1 to HTTP 2.5 LLAP. At that point, LLAP was a tech preview, and we saw 25x difference in runtimes with the TP-CDS 10 TB. Next, this was in 2017, we ran HTTP 2.6 LLAP, comparing it to the previous version. We saw 3x times of a performance difference. And right now, this in 2018, these are our early performance benchmark numbers, but we are seeing on par or even better performance. And I need to point out that this is with asset tables. So asset tables have additional transaction ID, row ID columns in the table, so we expected that to have some sort of impact on performance. So this was sort of a pleasant surprise and a good call to the asset implementation. So how did we do it, and what are our main contributions to this high performance? Our star, obviously, or you must have, if you were there on the Walmart presentation before this, this would not be any surprise to you, but it is LLAP, long live in process. So what is LLAP? It is a set of persistent daemons that you allocate on the cluster. They are given as part of the cluster is sectioned off on a yarn queue, and LLAP runs on that. LLAP, since it has a separate queue, you can schedule, you have the option of tuning the yarn cluster separately and LLAP separately in terms of fair scheduling and other parameters that you would want to set. LLAP has in-memory caching, and that's what is the biggest, one of the biggest performance differences for us. It saves the trip back and forth. For example, in the cloud, the storage and compute is decoupled, and if your data lies in the data lake, to go and read data back and forth would drastically improve affect the performance of the query. So in-memory caching helps us a lot on that front. LLAP sort of provides you like a relational view of the data, so it is not just limited to Hive. Recently, we would have heard about Spark LLAP. Spark is also planning to use LLAP for data access. However, LLAP doesn't store data. It reads its data from HDFS, S3, or any other data storage. So LLAP has executors and IO threads. So executors do the work of the query fragments, they execute that, they keep the CPU busy. The I/O is asynchronous. If you have I/O requests, they go and fetch the data from the storage. And the execution happens in the vectorized form. So we use the CPU pretty efficiently. Vectorization helps with integer comparison computations, filter evaluations. So vectorization is a big boost. Even we introduced the decimal vectorization last year in 2.6, and that has been a big boost for decimal queries that work with decimals. LLAP works with text, ORC, and Parquet. ORC and Parquet both are native support in the caching and vectorization pipelines. This is a very well-known, widely used architectural diagram of LLAP. So when a user submits a Hive query, it goes to the Hive server 2 through JDBC or ODBC. The Hive server 2 plans out the query. That's where the CBO sits. Divides the query into logical execution plan. That gets submitted to a Thais AM. The Thais AM which, then breaks the query into fragments and schedules it to run on the LLAP daemons. As you can see, there is a shared in-memory cache. So this is the sort of the game changer, like I said. If your data resides in the cloud on a data lake, as users query data, the cache gets populated. It is shared, so based on your workload, as one user, if you are querying any data that is hot data, the impact will be felt multifold across the queries. It's not limited to a specific user or a specific set of people. What else? Yeah, that's about it. So how much data can we cache? This was something that one of our customers, Walmart, pointed out in the previous presentation. So the amount of yarn memory that you allocate to LLAP, all of it does not go into caching. The executors of LLAP need at least 4 GB. Each executor needs about 4 GB of memory. So that sort of limits the amount of RAM that you can allocate or cache that you can allocate to the daemon. But LLAP also supports SSD caching, and SSD for a typical server increases your capacity of caching by 4 times, and this can impact your query performance tremendously, because if you have workloads, users querying the common set of tables, and as you cache more and more data, this SSD cache can be a game changer. SSD caches were also used in the HDinsight, the 100 TB benchmark run that I showed earlier. The LLAP caching is also very intelligent. It's decentralized. Like they've made it in such a way that we do not throttle at any point. So if the caching and the eviction of data is not decided by a central controller, each of these daemons works independently. So there is no throttling in terms of, and there is no admin intervention saying that cache this data or evict this data. It is columnar. You only read what you require. If you come from the data warehousing world, you sometimes see very wide tables. For example, the customer address table in TPCDS stores the addresses, and some columns are very wide varchar columns. So if your queries do not use that, if it was row formatted data, you would have to cache everything. In columnar, you only use the specific columns that the query uses gets cached. It is also automatic in the sense that, again, the user or admin doesn't have the control of saying, or doesn't need to say cache this table. It is adaptive. As the users query the data, those tables continuously get cached in memory. It is also additive in the sense that as new files or partitions get added to your data, the new portion gets added to the cache. It's not like the older data gets dumped and then a new version of the data gets loaded. So that makes caching very efficient and smoother. And the data is also encrypted. Well, in before it gets loaded into the cache, if you are using compression, like Orc uses compression, Parquet uses compression, the data gets decompressed, but it is loaded in cache encrypted. So that keeps the footprint small and the data is compact, so we can get the most of our memory, cache memory. There are two parts. The cache is also layered. There is the metadata caching and there is the data caching. So like Orc and Parquet have built-in indexes like the min-max indexes or the Bloom filters that you can create when you create the table. Those get cached separately and have on a higher priority, and then the data gets cached. So the reason why that happens is some queries can be directly answered from scanning the built-in indexes. For example, if you're looking for a specific customer ID, and if the customer metadata is cached and we know that it doesn't exist, then it just doesn't exist. The query can return immediately. It doesn't have to go and look for the data part of its of the portion. The cache is also coherent. It's ACID compliant as now we support ACID in HTTP 3.0. As the tables will get changed, the LLAP cache will get invalidated for that specific set of data pages, and the new data will get cached automatically with when the query accesses those tables. And I alluded to this before, we support text caching. As the users run queries on text, text data gets encrypted in the background efficiently, and then future queries can see the performance on the queries will improve. The thing is, there is a cost associated to converting a text data into Orc or Parquet. If you have text data in the cloud, your cloud vendor will charge you for the conversion and storage, right? So, but if you have LLAP, you do not have to go through that process, and that's why we call it the zero ETL, because you can directly query on the text data. So now I have a demo of a query. This is a TPCDS query 52. It's on one fact table and two dimension tables. I want to show you the effect of caching. Okay. Is this visible? Yeah. Okay, I need to. So I have already restarted LLAP. So this is a cold cache that I plan to show. So I start beeline. So this query typically in the cold cache runs in about 20 seconds, under 20 seconds. And so you will see about 3 mappers, one for the fact table and 2 for the dimension table. Should be coming up now. Okay. So you will see the query took 28 seconds. If I scroll up, I have set Hive exec print summary set to true, so it will print out the summary of the query. I'm looking for the LLAP IO summary right here. And you can see that for map 1, which was for the fact table, the data hit is 0, and the data miss was about 6 GB of data. So we'll go back and rerun this query. And this time it should come back faster. So it took about 10 seconds. So from 28 to 10 seconds, it's like a 3x performance difference. If you go back and look at the LLAP IO summary, sorry, that's it. Yeah, right here. So you see map 1, completely all the data was in memory, there's 6 GB of data, and so is for the dimension tables. The DAG itself actually ran in 5 seconds, so the remaining was just submitting the query and some compiler times. So that was the demo of the LLAP cache. As you can see, the performance was improved multifold by simply caching the data. We go in the presentation mode here. Okay, so for the cloud, there are some more things that we need to consider. Cloud storages have the models, it's an object store, it's eventually consistent. So when we started this back in 2 years back, we noticed that with S3s especially, we had issues with with directly listing, and Hive works a lot with HDFS files and listing. For example, when you add a new file or when we finish a job, so we do operations that list the directories. This can cause issues with the wrong results, for example. So S3 guard was put in for Amazon S3. We recommend that people use that. This prevents the problems of using the cloud storage. Along with that, there were a lot of performance improvements that were done for running the Hive queries, like for split computations and in generating the computations and optimizations while reading. For example, permission checking. We do not do file permission checkings and directory permission checkings if you're running this load in the cloud. Google Cloud Connector is coming in HTTP 2.6.5. There is the talk I mentioned about is going to go through what optimizations we did for Google. And the Azure also ADLS has optimized Cloud Connector. This was done by Microsoft and HortonWorks together. So you can get faster access to your data in HDinsight. So that's for LLAP. The next thing we want to talk about is data layout. There are things, these are the things that you can do to improve the performance of your queries. So first is partitioning. This is a very common adage that if you have data that you can partition, or if there is a column that has a fixed number of values, and for example, or a chronologically increasing column like a date, for example, then it is better to partition the data. It helps the queries in 2 ways. One is if you're filtering on the partition column, it can do static removal of the partitions, or partition pruning. Or if you're joining on the partition column, we can also do dynamic partition pruning, so which means that the date values or the partition values come from the other table at runtime and can remove the scan partitions from the source table. So that's a very big boost if your queries follow that access pattern. The other thing you can do is bucketing. You can bucket your data on a specific column. What bucketing does is it hashes the column and all the values the same hash values go into a single file or a bucket. If your queries have equality filters on this specific column, then bucketing is a good way to go for it. The other option is Bloom filters. When you create your awk tables, you can also specify a Bloom filter, and the equality predicates can take advantage of that. The other thing you can potentially do is you can sort by a specific column in your data. So like I was talking, Orc and Parquet, they both have built-in indexes where we store the min and max values. So the data is divided into strides, and for each of those strides, we store metadata of that specific data along with the data itself. So when you sort your data by a specific column and you have filters on that column, it helps to skip while scanning. It helps to skip chunks of data, and I have an example of this right here. So here we have an ID column, and you can see if the data is unsorted, then your min max or your index is all over the place. Like the first one is 1 to 100, 2 to 25, and so if you have a query that queries on the data layout, like in the green section, all those stripes or strides will qualify for the scan. However, if you have sorted by ID, then only the second section, because you applied the filter on the metadata, only the second section will qualify. So this not only reduces the amount of scan, it also reduces the data that you will cache. So it's quite effective. There is a catch here on HTTP 3.0 with ACID. We don't allow bucketing, and sort by is not supported. However, in that case, the one thing that you can consider doing is using materialized views. This is a new feature that is coming out in HTTP 3.0. The concept is kind of known for a while. It's supported in many database engines. The idea is that you can speed up your aggregate queries by pre-aggregating and storing the results, or pre-joining and storing the results. When Hive, the support, the way it's added is that the CBO will the optimizer automatically recognizes what queries can benefit from the materialized views that you've created, and it will do the rewrite. It's also not an administrative nightmare, because there is efficient maintenance of these materialized views. As the new data comes in the tables that are part of the materialized views, it can be done, incremental refresh can be done. And you can also define policies, in the sense that you can say that after 5 minutes or after every 10 minutes, the materialized view should become stale, or it only becomes stale after there is a data change, or how much of the data change happens. The materialized views can be stored in Druid. Druid is a fast processing engine for OLAP. So Hive has support of storing the materialized view in Druid, and then exposing the data through a storage handler. So if you store the materialized view in Druid, then you don't even actually have to pre-aggregate, or it can do more aggregations over the pre-aggregated data, and it can speed up the OLAP queries significantly. So I have an example here. This is using clickstream data. So imagine if you were Netflix or a website where you want to see which users came on a specific day and how many times did they visit. So let's say your source table is called clickstream table. It has the user, and it is partitioned, let's say, by date, because as the new data comes, you are creating new partitions. Then we created a materialized view in Druid that selects the user and the date and a count of the number of times they visited on the source table, and you group by the date and the user. And let's say then your query is something like count distinct of a user and the count of visitors. So you're trying to see how many distinct users came and how many times did they visit the website or visited a specific video or Netflix. And you give a date filter on it. So this can be rewritten or will be rewritten by CBO as a select count of the user itself. So count distinct gets rewritten to count of user and the number of times they visited. The date filter that you see over there, that was 18th of June, gets applied to the partition, to the group by clause that you see in the group by date. So it takes out, it only reads that part of the materialized view set which has that date filter set. So this way, and since this is running in Druid, you should expect like sub-second performance. So this is one of some sort of an applications that of how people are using Druid and materialized views, or we potentially see them using. So that was for the data layout. The next thing I would like to talk to you guys about is the optimized query plans. So no matter how good the execution engine be or how good your data layout is, if your plan is not as good or the query is planned poorly, the query will not run efficiently. So we'll look into some key features that we've done in the optimizer. So Hive comes with a very comprehensive cost-based optimizer. It is powered by Apache Calcite. It needs statistics. The statistics are gathered generally on insert if auto-gather is on, but those are table statistics. You should collect column statistics. If they are missing, you will see that in your explain plan, there will be, it will say a keyword none, which indicates that the column stats are missing. What cost-based optimizer does is obviously join selection, join reordering. There is predicate pushdown. So if your with the BI tools, they are notorious about the way they generate the complex expressions and redundant expressions. So the CBO is smart enough to derive new predicates, remove the ones, do constant folding, and all those sort of things. So simplify and also push down predicates into the scans. So we can scan as less data, or we can filter data at the source before it goes through the operator pipeline. Also, there is a lot of general query rewrite, like union rewrites and subquery rewrites. These are things that are quite people in the database world are very familiar with. It's all part of the Hive CBO. So the predicate pushdown goes into the metadata, that is the built-in indexes that is stored in the org or parquet. Recently, we've introduced HLL statistics. These are bit vector stats from which we can do a better job of computing the distinct values, so we can come up with better plans. And then we have a feature called shared scans and dynamic semi-join reduction that I'll talk in the upcoming slides. So what is shared scan? So a lot of BI tools, and in fact TPCDS benchmark also has many instances of this. You would have references to a specific table multiple times, and sometimes the same set of filters also repeat on those tables. So which is fine if it's a small table, it probably doesn't impact performance as much, it's just more of an annoyance. But on fact tables like store sales, if you have multiple occurrences of store sales, then this can really add up in the query runtime. So shared scans identifies these common patterns in the query plan and replaces it by a single scan, and then feeds into the multiple portions of the queries the data that comes from the single scan. This drastically reduces your I/O, and it's again, you can see that's a big win, especially in the cloud. Because you don't have to go back and forth. I mean, if the data is cached, it's fine, but sometimes fact tables at larger scales, all the data may not even be cached. So this can really add up the query runtime. So when we tested in shared scans, this is one of the queries that was one of the candidate queries fit well for shared scans. In this, this is query 28. It has 6 instances of store sales. And it's doing average, it's doing multiple aggregates over store sales. The filters, if you notice, it has differing filters on 3 or 4 columns. It's looking at quantities from 0 to 5, quantities from 6 to 10, and there is the other filters are slightly different. But this can also be improvised. Previously, we were doing 6 different scans of store sales, and each of those scans had those set of filters, like B1, scan 1 had B1 filters, scan 2 had B2 filters, and so on. And this query used to run about 800 to 1,000 seconds. After shared scan, what happened was we replaced all the 6 scans with a single scan, and all these filters were ORed together. So B1, the filters from B1 or B2 or B3. And so you still don't select the whole of store sales, you still are bounded by for instance, in here the quantity probably doesn't goes over 30 because B6 was up to 30. So you still apply those filters, but then there is a reduce sync operator for each of those scans that will do the further filtering and then pass it on for the join operation. So that query went down from 800 seconds to 200 seconds after shared scan was applied. That was about 4 times of a difference. There are other candidates in TPCDS. Query 64, for example, it has many fact table joins. It has a catalog sales and catalog returns join, and it repeats it twice. So those, it not only just the scan of one table, shared scans can look for common join patterns and replace that as well, as long as the filters match. So this next is dynamic semi-join reduction. This is actually one of my favorite features because of it kind of sometimes surprises even us on how it impacts the query runtimes. So what is dynamic semi-joins? The dynamic semi-join is where when you're joining 2 tables, so the typical process is you scan one part of the table, and then you pick up the values from that side, you scan the other side, and then you join them at the join operator level. So there is no, so whatever, if there are table filters, those can be applied at the scan level, but there's nothing much beyond that, right? But if, let's say, your join is very selective, then and that if there was a way you could transfer the values from the dimension side or the smaller table, or let's say the more selective side, into the larger scan and dynamically filter it before it even reaches the join operator. So I have a query here. This is joining sales with time, and the filters on time is on year and quarter. So the portion in yellow is a typical join where you scan time, you filter on those values like 2014 and Q1 and Q2. You feed it to the reduced sync, and then you join sales and the time. As you can see on the scan of sales previously, there was nothing much you could do. You had to scan the entire sales table, right, because the user hasn't specified. However, with semi-join reduction, there is a Bloom filter that is created at runtime. So the time IDs that were generated after the filter was applied on the time get converted into Bloom filter values that gets applied to the scan of sales. And this reduces the scan tremendously. Again, because we have the built-in indexes, we can do min-max filtering on the sales side. So we remove the, in batches of 10,000, we can remove the amount of store sales, amount of sales that gets scanned, sorry. So how does this work in a star schema scenario? So this is just one example I gave you with one dimension. A star schema has multiple dimensions. It can be combined. So for example, here, if you see the left side without the dynamic semi-joins, all the dimension tables go to the join, and then the fact table joins. With the dynamic runtime filtering, a dynamic Bloom filter gets created from individual dimension tables after the filters have been applied to each of them, and they get applied on the fact table. So the fact table scan, the number of rows that flow from the fact table up to the join operator are significantly reduced. So another example from TPCDS, this is query 72. This was an interesting query. This was looking for items in catalog sales that were ordered by customers and then shipped 4 days later. And then it was joining to inventory to see if the items existed in the inventory, and if not, then was that the reason why they were delayed by 4 days in shipping. But it also had some date filters on it, so we were only looking for a specific set of in a month or something like that. So previously this query used to run in 1,000 seconds because what we used to do was a join of inventory and catalog sales, and then after that we would find out that there was really no items that qualified. Now we found out that for that specific date range, inventory has 0 items that match. So the query came back in like 145 seconds, which is like a 7x difference. And that's why I said this is sort of one of my favorite features, because sometimes it can, even having statistics may not be able to give you all the answers, but with dynamic semi-joins, we can fix those issues while the query is running. Query result cache. So this is a new feature in 3.0. What this feature does, it caches the query and the result set. So for concurrency or for common query patterns, this is a big plus. We have in our experiments, we have seen sub-second performance. The query results are stored in HDFS. The query cache is security policies are still in force. So one user does not see the data from if he is not authorized on those tables, will not see the results from another user's runs. And I'm actually out of time, so I'll quickly go through this slide. This is, I think, my last slide. We did one experiment with 2 queries. This is with 500 users running this concurrently. With one Hive server 2, we were able to achieve 58,000 queries in 2 hours. And the 97% of the queries ran in 5 seconds. So the fastest query was less than a second. If you have ETL running at the same time, so those tables are changing while there are queries running, this is sort of the query latency graph we got. So wherever you see those the dots that are going higher, those are the cache misses. So the ETL happened, the tables changed, and then as the queries ran and the new data gets cached, and then you can see the latency comes, the query performance improves again. So all in all, this is the whole package in HTTP 3.0. We have ACID, materialized views, we have statistics that are improved, constraints. There's also workload management. I know there was a discussion in the previous presentation on that. And there's query result cache. Questions? And I'm out of time, so if you want to step out and ask me questions, I'm getting looks here. So thank you, guys.